Hi, happy to present SNOW, Spatio-Temporal Scene Understanding with World Knowledge for Open World Embodied Reasoning. To be able to interact with the physical world, an agent needs to be able to understand space and time for embodied reasoning. Hence, what objects are around it, where they are located, and what has changed over time. Vision language models provide rich open world semantics and world knowledge, but lack spatial and temporal understanding. On the other hand, geometric perception models provide precise structure, depth, and motion, but are semantically sparse and only provide closed vocabulary label sets. There are some existing prior methods that try to tune VLMs on the spatial or temporal training data, or provide explicit graph structures for 4D and 3D understanding. However, they do not combine open vocabulary understanding, metric 3D features, temporal understanding, and object centricity. Object centricity in this case is particularly important because it bridges the gap between the language that naturally describes things as objects that move and interact with each other and the geometric domain that provides these objects their positions and their spatial and temporal features. SNOW provides such an object-centric interface that is queryable by a VLM to reason about objects and their movement in space and time. It consists of multiple steps. After clustering out region proposals and segmenting objects, each object becomes a small set of so-called step tokens. We will come to that step tokens in a second. Each step tokens contains spatial and temporal features that are then accumulated in a 4D scene graph through a global representation. This global representation is consistent in time and provides an interface that is naturally queryable by a VLM as it has the same token language the VLM already has. Step tokens provide a representation that describe an object with a handful of different semantic, spatial, and temporal tokens. Image patches underlying the mask provide the semantic information. Centroids describe where the object is in 3D space. 3D Gaussians describe the shape of the object, and the timestamps describe when the object enters and left the scene, or when it had a certain positions in the scene or a certain shape. These step tokens are accumulated in a globally consistent object-centric 4D scene graph. Nodes in these graphs are objects holding the step tokens. The robot itself is a node too, an object that moves through space and time. The global consistency is enabled by a SLAM backend, for instance KISS-SLAM for LiDAR or Map Anything for images, depending on the specific 3D representation and points used. Additionally, a reasoning refinement step is conducted to sort out implausible movements, shapes, and objects that would distract the reasoning process. For instance, a pedestrian that has moved in the speed of 100 kilometers per hour would not be plausible, as a human cannot move in that speed. Through this representation, SNOW achieves state-of-the-art or near state-of-the-art results in many spatial and spatio-temporal reasoning benchmarks. Our ablation study shows that this gain is mainly due to the combination of all aspects into this unified 4D representation. We also show that SNOW is backbone agnostic by providing similar gains with different VLM backbones on the same benchmark. In our qualitative results, we show that SNOW can be used for various downstream tasks in the spatial and spatio-temporal domain. For instance, 4D reasoning, pointing in space, and LiDAR segmentation. Our key takeaways are first that structure beats scale. A small model can outperform a much larger one with the right representation for embodied reasoning. Additionally, you don't need to fine-tune VLMs necessarily for spatio-temporal reasoning. The harness, the representation provided to the model, can have a much larger impact. Third, our world model is naturally queryable by a VLM by providing an interface that grounds language and geometry through object centricity. There are still some open issues. For instance, we did not account for latency with our method. Latency grows with the number of objects. Additionally, global motion is captured well, but fine-grained deformation is less well represented. In the future, we want to develop task condition filtering and token compression for 4D representations such as snow. Additionally, we would like to use snow as a labeler to train 4D aware models that are able to infer 4D representations directly through one inference step. Thank you for listening and looking forward to meet you at our poster.